Last week we had a CPOP 2024. During that meeting, SAR released the new data from BES-I. So we decided to have a discussion here. So Xin from RHIC will present star data, especially for search for critical point. So Xin, please go ahead.
Thank you, Nuke, and also the HIT committee for the invitation. I'm very glad to talk to the recent measurement of the precision studies on the net-proton number fluctuation, aiming towards the search for QC critical point. So this actually is long-awaited results, and I would want, before I start, I want to give many thanks to a group of a team of very dedicated people. Actually, I highlight a few. That's our kind of core analyzers: Igor Huang, Bapa, Fans. This red highlighted is red are graduate students, and Ashish here locally. Yuzhang are postdocs. So those are the people who really do all this dedicated work over the last I think a year or two, and make this results happen. And thanks, and also thanks to the whole STAR collaboration for the strong support in terms of resources and also the reviewing process and our theory colleagues for lots of discussion. So let me start with just a quick outline. I'll briefly introduce what we are doing to search for the QCD critical endpoint and the observable we're using proton net-proton cumulants. And we'll talk about the BES-I program, the RHIC. And the main talk covers the results is the precision measurement from the BES-II collider energies from 7.7 to 27 GeV, including the net-proton cumulants and their ratios, the proton-antiproton factorial cumulant ratios, and our end of summary, and with some discussion on what we plan to do next, as well with the high statistics samples. So if we have our collisions, our target goal is really to study the QCD phase diagram in a wide temperature and density region. If you look at the evolution of our understanding of the QCD diagram over the past 4 decades, those are all the figures that grabbed from the long-range plan document. You can see the evolution of the understanding of the QCD diagram. Certainly, first impressions become more colorful, but actually there are more critical things. One I want to point out is actually in the 0 μb region. You can see the TC, the critical transition temperature, the various, and now it converges to a very precision understanding through the development of lattice QCD and also experimental data constraints. So in the meantime, we know with the development, we know this is now at mu b equals 0 is a crossover, and you can see this and also based on the symmetry that we know that high mu b region, that expectation is first order phase transition. So that become this critical point concept can start to emerge, and this become the focus of the RHIC BES-I program over the last couple of decades. And so the last long-range plan produced this plot, including this is still put in question mark that we are looking for, and all the experimental program in the BES-II covered from RHIC collider and fixed target energies, trying to cover this region. And certainly the location of this is to be determined, and also even including the future experiment. And that we are come to this in the end. So the QCD critical point, as mentioned, at the mu b equals 0. And now we have a reasonable solid understanding. The lattice QCD provide very precision calculation. This is a crossover phase transition, and this critical temperature or phase transition temperature is also very precisely determined in the lattice QCD. I would also point this is actually not just development QCD. All our experimental observable measurements actually is quite compatible. Although we're still looking for, I would say, it's probably direct evidence on this crossover phase transition. But all measurements are very compatible. Well, if you push this to the high and finite mu b, and in the real QCD world, there's a lattice QCD calculation. It's a famous sign problem using the traditional Tyler expansion method. Although the lattice group is trying to push harder on really how they can do it. And also for long-range plan, like a couple of years ago, that our understanding this lattice can predict this critical endpoint in the QCD physical world is beyond 400 MeV, or the mu v over t is larger than 3. And New mentioned the CPOD meeting. Actually, there was quite very active development over the last, I'll say, few years. I mean, more intensive in recent years in the theoretical prediction on the QCD critical point. Since we have still challenges in the full QCD lattice QCD calculations, there are various approaches that already has been tried to do the prediction of QCD critical point, including in the lattice QCD, you try different resummation methods, but you need to consider also your cutoff. And but there's certainly lots of efforts toward this. And one also rely on these various functional methods to also push the QCD calculation to a high mu b. Even the holographic method also in this trial. The recent predictions actually interest me. They all point towards the QCD critical endpoint in the region of, although there's large uncertainty region, those points are prone to different calculation. But this is a kind of more towards the region. You see around 600 MeV, but it's still with large uncertainties. I want to point out one thing is also, although there's various different methods tried here, but the constraint they have is always at mu b equals 0, they fix different calculation or different observables with lattice QCD. But extrapolation is based on various assumptions or approximations. So that's always need to be tested. So this is still.
What is BHE?
This is the black hole, holo engineering, holographic calculation. This is one of the calculations. Actually, there's multiple calculations here. There are various also in the range.
Critical energy is so low.
Yeah, this is only one of the calculations. There's quite a few calculations that sit around here as well.
What do the orange and yellow bands indicate?
I would suggest I think it's the uncertainty associated with this lattice QCD extrapolation based on different.
So that's lattice uncertainty.
Yeah, lattice uncertainty.
Perhaps lattice uncertainty is limited below 300 MeV. The extrapolation is just extrapolation.
Yeah, well, yeah.
We cannot blame lattice. Blame lattice at 600.
Well, you take the pseudo-critical line; it's measured up to the 4th order, and then you see the mu squared, and then the mu to the 4th, and then they just extrapolate this out as a polynomial.
Based on whatever function from that. Yeah.
And one would expect if there's a critical point, it should sort of sit on the crossover line, right?
So I have a question about these ADS things. I mean, ADS, at least his initial, like, didn't pay a lot of attention for a while, and his initial manifestation was conformal. So how do you get a critical point out of a conformal theory?
Based on my understanding, they claim that it's not really conformal is not really needed. I don't fully.
So this is the engineering part. They break conformal symmetry.
Yes.
To which extent this is then?
So this is ADS. so this is ADS plus the modeling.
Exactly. Absolutely.
So how seriously do we take it?
Well, you should take it seriously because he has these model parameters and he uses a Bayesian analysis.
I'm sold.
The tricky,
You just have to say the magic word.
yeah, the tricky part is all these ancestors that put the constructions of this function. That is.
Okay, so this is somebody's model tacked onto.
Yeah, but I mean it's amazing, right? So he has all these priors, and some of them don't have a critical point, and then he fits it to the lattice data. Yeah. Actually, I learned you have to call him George because he's Portuguese. But anyway, and then he does his Bayesian thing, and what's left over are a bunch of solutions which all cluster around. I mean, he just showed a few points. Bunch of solutions which all cluster around. What was it? 100 MeV temperature, 600 MeV.
Yeah, 600 MeV and 100 MeV.
So
this is
so
actually
it's funny, right? But that's all.
Which Jorge or George?
George Nohona from UIC.
Perhaps the most severe issue is it's not really black hole engineering. In two of these approaches, there's no barrier.
Yeah, that's my second question. How do you get baryons out of the AES?
Instead
More engineering.
instead of fitting the lattice data, well, maybe they should fit the real data instead.
That I think is a very.
That's actually one of the things that actually I didn't want to this
almost
Sorensen.
So
APS.
Yeah, APS purely based on the thermodynamic scaling and fitting the repeat depends on the data. But that's also
There is another issue, but baryon is issue series for APS approaches, Agnieszka or Sorensen. They equalize the momentum space rapidity to space rapidity. That is, to me, especially in low energy, I'm not sure that works. In LHC maybe work fine, but there is a bigger dent. I do not understand.
What's magic about 300 MeV for lattice? Is there some fundamental reason they can't go beyond? Is it computing, or is there some?
I think it's computing. If you put next 10 years computing resource electricity onto that, they will go further. I'm pretty sure. According to
I think it depends on popular ratio.
You don't care about global warming. You can solve this problem.
that may solve the global warming if you have a lattice result.
My understanding is one of the things also certainly 300 MeV can see this ratio go beyond 2, and if you do the expansion, they really depend on the cutoff, whether this still converges or
tenth order.
So there was a
even
very,
cut a tenth order whether it converges is still a question.
so there was a very interesting talk by Borsani from Wuppertal, who pointed out when you do this higher order cumulants, you get like 10,000 terms you have to calculate. 5,000 of them are positive, and the other 5,000 are negative. So there is actually a sign problem. Although you don't have a sign problem, there's a sign problem. So that's why the error bars, when you higher the cumulant, so it's not clear whether you with a bigger computer can eventually solve it, right? Because
you take a small difference of large numbers,
and then I don't know and then the number of terms grows rapidly with
your 10 years was just a long time, or is it really 10 years?
I just heard that NPR this morning, 10 years of computing will take lots of electricity.
Exactly.
I think this is one of, this is a problem, I think, one of the problems I would like to see. So, right? You may get a critical point.
So, the experimental side, I think what we are trying to do certainly provide precision data that's also provide input to theory and understanding on how we can looking for this, how we can determine the existence and also location is critical point. If you think about this is just a very simple idea. At any critical point, if you have a formalized or infinite system, the correlation learns to diverge, or susceptibilities also diverge. Susceptibility is just the derivative with respect to the various chemical potential. And certainly this was be probably affected due to the finite volume or size, system size in the heavy-ion collisions. But this is still the idea that if you're looking for the conserved quantities and also looking for the various order of moments of this distribution, like baryon strange, and those are in the model calculation are very sensitive to the system correlation lengths. So there should also kind of be sense there's fluctuation that induced by this critical point. And some of those quantities also are directly related to the susceptibility ratios that can be calculated from discretity. So that's one thing that you have a first order comparison to the first order principal calculations. So the observer looking for like a various order of moments. The first order is mean, second order variance, third order skewness, and kurtosis. These are also you can relate to the multiplicity cumulants, and the notation we use here, they're using C as a cumulants for various orders. And in the measurement, we're also looking for the factorial cumulants, and those are proposed to be more sensitive to that particle correlation at that fixed order. So we're looking for all different variables. So expectation from the third side is that if you have a critical point in the system, and those are the model predictions on the fourth order cumulant, they should the red region is negative and the blue region is positive. So if you scan the energy, this is the red yellow lines are supposed to be the phase-out line. Or
I'm sorry, what are the axes on this plot?
There's no axis. That's presumably the T mu b, but no scale. T and H or R and H.
Oh, R and H.
R and H, but
T and U for.
it's a rotative. You can imagine some relate to the T mu b composition of the T mu b, and any first order phase transition with a critical point. And suppose there's a your phase-out line go this way, you should go from an energy. When you scan energy, it should go from high energy to low energy. So you would see a negative value and then a positive value for this critical point induced by this critical point. So that's kind of a conceptualized. That's a signal that we're looking for, a oscillation, and those oscillation with respect to some baseline. And this is I want to we'll come to this probably later on. In the early studies, we will expect this baseline with this scaling or Poisson baseline and maybe a flat line, but now we know this maybe also need to be carefully studied. Another thing is this oscillation feature is we're looking for this oscillation feature induced by a critical point, and that should start from some baseline high energies and return to baseline in very low energies once you go past that critical point. Okay, so this is the features we're looking for. So the BES-I measurement, we see this is the Net-proton C4 over C2 or kurtosis time variance as function energy. That's the exact variable I showed in the previous slide. And the data points are shown in the red one. You can, including the collider energy and also one measurement from the fixed cycle energies. You can see there's a hint of non-monotonic behavior. This is the way we look at the statistical. This is at the order of roughly 3.1 sigma. And originally we were thinking of a baseline just a 1, because this is in the scale and Poisson statistics are just 1. But later on, there are various model studies show that actually, due to the baryon conservation, this baseline should have a decreasing trend as you go to lower energies. So those BES-I give us some kind of interesting results, but the statistics is actually still large, particularly in the region of from 20 to 7.7 G. That exactly what motivates us to go for BES-II, and the green band actually show the project uncertainties, and will show the results with the new variables.
What is the kink of the Yarkand calculation?
That's a very good question. Actually, I don't know. It's a very mystery. I think the Yarkand, it is real from the calculation. Exactly 27, 25, 27 dB. There's well, I don't want to speculate too much, but there's a different, some algorithm that get switch on around the energy region for the Yarkand.
So this is some physics behind, not the statistical.
There is some physics underlying in the model that is in the model that creates. And yeah, whether it's real or not true, it's certainly need to be discussed. This is the only Yarkand model that we often show that is one thing that you can check. That's so-called you can run this event by event calculation and use exactly experimental ways to measure fluctuations, including the kind of polycentric CX and total beams, which I will come to this later on. So that's where you can try to compare to without experimental data. The good thing is that you can see is more or less, except for these energies, generally they're consistent with this hadron resonance with the canonical ensemble. This taking into account the baryon conservation. I didn't have this part didn't have a Melodius hadron calculation, but it's also all similar in this trend. I'll show this later. The general feature of this trend is dominated by the so-called baryon conservation that we now know that is could be a modified reference or baseline for comparison to compare with our data. But precisely that still need to be, or we need to see from our theory friend to the calculations. So the BES-II program basically is focused on energy at 27 GeV and below. And initially we have collide energy down to 7.7 GeVs. And we also added on the fixed circuit program that covers also the energy region down to 3 GeV. So if you look at the mu-B coverage, this is a coverage starting from roughly 150 to like 750. It's a pretty wide mu-B coverage. And in today's results, I'll be focusing on just the collider energies. I'll, in the end, discuss about some prospects what we're looking for the fixed circuit energies. And really, the BES-II really happened successful. That we need to really thank the RHIC side to develop this low energy electron cooling that improved the luminosity dramatically. If you see the good event rate in the BES-I and BES-II, you can see across different energies increased by factor of 4 to nearly 8 or 10 in different energies. So that actually significantly improved our statistics in the for our experiments. So the 7.7 GeV, and you can see we completed within the 12 weeks for the data taking, although the initial estimate is like 20 weeks. So the collider, the machine side is also kept optimizing all the performance that really make this happen. So to the event sample that we used for this analysis, I just put this table. We have 7 energies for this new data from 27 to 7.7 GeV. And the BES-I data sample and BES-II data sample, you can see there's the overall statistics is about a factor of 10 to 18 increase in terms of statistics compared to
17.3 matches the SPS.
Yep, that's one of the reasons that choose this. That there are 2 new energies, 9.2 and 17.3. That.
But you never show an SPS point on your. It was
never
never analyzed at NA49?
They don't have the statistics yet.
And,
For the higher order ones.
No
acceptance is.
Wait, they've got an NA49 as a full base space, not enough?
There's no acceptance.
Surprised.
They have a result on the second order, but not on the fourth.
Yeah.
So they cover vast base spaces.
Look at the proton PID.
Oh, it's a proton PID.
You look at the.
So to really make good use of this high statistic, we also did upgrade for star detector to enhance our detector performance. And a few, 3 of these major upgrades are in the TPC that really push down to the tracking in a wide pseudo-repeated region, expanded the pseudo-repeated coverage, and push to low PT. This is actually one of the key, have a very key impact in our new results. Other 2 measurements, the NCAP time flight and EPD, also have a benefit our other beam scan 2 programs. And I'll come to the end regarding the NCAP for the fixed circuit program later on. So the performance of detectors also shown to be very good, and the ITPC gives the extent repeated coverage from roughly -1 to -1.5, -1.6. This is a reconstruct tracks. And with this, also you have more measurements in the TPC that improve the momentum and also the DDX resolution. DDX is used for the PID, and that really improve also our particle identification. And this to compare the BES-I and BES-II. The ETOF show also good timing resolution and matching efficiency. EPD is also significant improvement in terms of event resolution. So particle identification is one of the key things, and for the in the star we have over the many years we have demonstrated we have a very good PID for all various particles, stable hadrons, light nuclei, resonances, string hadrons, even hypernuclei. So particularly for this analysis, the protons are identified through a combination of DDX and the time of flight. You can clearly see the clean identification of protons in this plot. So but with that said, and for the analysis, first you want to determine the centrality, and this is actually this is still a continued discussion regarding the clearance centrality determination in the fluctuation measurement. We use the charge particle multiplicity and Fluctuations global model to determine the clearance centrality that's being widely used in the hadron experiment. For this particular analysis, certainly we need to exclude protons and protons just to avoid self-correlations. And this is by just using the DDX and to apply a V2 cut on this. In the BES-II, because of extended rapidity, we can now have two different. We present two different choices, actually multiple choices. But in this results, we have two different choices of the centrality determination. One is so-called BES-III is using all the charged particles within pseudo-rapidity less than 1, excluding protons. And the RHIC, this is because of the ITBC enable us to expand the rapidity coverage to 1.6, and we define this called RHIC. This RHIC is the same definition as we use in the BES-I analysis. On the right figure, you can see that the distribution from the BES-I and BES-II, BES-I RHIC, BES-II RHIC, and BES-II RHIC. You can also see there's a difference still between the BES-I and BES-II. This is because of also the tracking efficiency improvement due to ITPC. So even you use the same definition, we're still accepting more tracks within the same acceptance. While the RHIC, so clearly the expand acceptance improves this a lot. So the multiplicity, actually the range, determines so-called the central resolution. If we see this kind of ordering of the RHIC from BES-II larger than BES-II, from RHIC and larger than BES-I RHIC, you would expect that our current measurement with the BA-RHIC would have the best central resolution.
So what is roughly the ratio between the RHIC for BES-II average multiplicity inverse of 0 to 5% to the old BES-I? I see here 800 to 600. Is that no? That's probably not even right.
Oh, sorry.
The mean multiplicity. You take your 0 to 5%, and what is the average multiplicity which you measure?
In the top 5%, this is top 5%, right?
Yes.
The average, I don't know, is probably on the order of
700.
750 or 7.
And the old one, this is about half. No, this is.
Old one would be this plot. Is BES-I one is up. The cutoff is 600, so it's a 500 level.
Okay.
We need to find precise.
Yeah. That would be good to know.
Yeah, I think it's roughly scale. You can maybe just look at the cutoff end.
Yeah.
Scales. Yeah, Peter.
19 GPM is similar to SBS, so I think this is reasonable as you go down. So going back to when we were all young and trying to figure out how to do these kinds of experiments, this idea of centrality, it doesn't obviously have to work, right? How do we know that multiplicity is correlated with geometry? And for me, the convincing evidence is experimental, and it's correlating, and you can do this at high energy, you can correlate, some global observable multiplicity, in the central region with something far away in phase space. And you have these beautiful plots of beautiful correlation. If you have high multiplicity or the ZTC kind of makes this horseshoe, you have a very tight correlation which you can understand, which has to come from some gross feature of collision geometry. There's really no other way to explain it. So that's data, and you see this beautiful correlation, and that's convincing. So for SBS energy is fine, we did that, but as you go down, not 19 but 7, is there any similar test to try to verify that Glauber is fine, but it's a fit, that this idea of centrality still makes sense as measured using multiplicity?
So maybe I can comment one thing regarding looking at the different detectors. There could be there was still a continued discussion in the start whether the forward reading detectors can be used together.
Right. That would address it.
Not very far off. ZTC will not be working.
You do what you can.
Yeah, but EPD, that's one of the things that potentially can help, but that's still under investigation. Second thing regarding the you mentioned the centrality. I forgot my. Yeah, I'll come back maybe.
Like a senior movie.
And there's also not only this, I think you mentioned it, but it's good to stress it. Not only difference in rapidity coverage and pseudo-rapidity coverage, but also in PT cutoff. So she mentioned that the improve of tracking, but because we went very low to the PT, we recover much more tracks than we had before. So it's not only Y, but also PT.
I'm asking a physics question whether multiplicity is correlated with geometry in this precise way.
Yeah,
Exactly.
and now I realize what I'm trying to say in the second. Indeed, this is the one thing. The second thing is we did actually look into model study like URQD and look in the same quantity we measure in the data, and then try to understand the centrality determination for this. There's certainly a strong obvious. There's a very obvious correlation for this quantity with respect to the impact point and also number of participants. And the complication of this analysis eventually it comes down to really there's a so-called this volume fluctuation. Basically, even you use any quantity to determine the centrality, you have finite the geometry that the system could fluctuate within the system. And this is always a continued discussion with fluctuation measurements. What we do now is trying to using the models, and that's why Xin model become useful. Is trying to currently using this quantity, we can use any other quantity later on determining their better, and then to look at this variable and then the measurement across this using the same definition of this observable and also all different features, whether they make sense or not. And so that's also one. I'll show actually one of the studies we see in terms of centrality impact on the cumulants and cumulant ratios. So I mentioned the proton PID, and it's pretty. We have a very clean identification protons from across all energies, and here actually this is a plot that including both in terms of pure proton purity and also the acceptance. So we do the identification for the low momentum using TPC. That's a standard technique where the DDX can separate protons from others, and our high momentum is combined with the baryonic flight, and this cutoff is just one choice and to ensure the high purity. The number, this windows show the analysis window, and the background, this color distribution shows the proton acceptance. That's tricky part. This acceptance generated for events at VZ close to 50 centimeter region, where it's at the edge of our acceptance. You can see this analysis window is all within our acceptance uniformly. So that's one good thing. We talk about if we can push this further down in terms of rapidity, then one has to reduce the VZ region. Otherwise, you will start to see the acceptance holes, and then we'll come to this in the.
What did the ITPC is on the wings here?
Yeah.
So what did it bring eventually?
Well, in the BES-I, this was getting much closer. This is getting this edge corresponding to your eta coverage, and then it get pushed further down with ITPC. We should have a plot with the BES-I. I have another plot in the end to show the BES-I, and they show quite it's a narrow coverage compared to BES-II. But here, what I want to show is we have a uniform acceptance within this our region and proton purity. We ensure actually even beam by beam has close to 100% in all acceptance region and all energies. So BES-II brings us better statistics. If you look in the cumulants, the statistical error bars certainly this is simple, just a square of n dependence. But in the meantime, we have roughly 10% improvement in terms of tracking efficiency. This actually has also impact in terms of statistical on the cumulants, because the cumulants also depend on your efficiency correction values goes efficient to the power of some alpha depending on the order. And so this is in combination, this give us a reduction in terms of statistical error bar in the samples and G is factor 4.7 and the 19 G is about 4.5. And also we have a better now systematics as well. The tracking efficiency with the improved efficiency now uncertainty also gets significantly reduced to roughly 2%. And the tracking and the better performance give us a better control on the background and also the PID. This all lead to the improvement in terms of the systematic errors. The systematic is reduced by about factor 3 to 4 compared to BES-I as well. So I'll come to the discussion, the resolution in the centrality when we present the results. So now I start to show the results, and those are all the cumulants, C1, C2, C3, C4, for different energies, 7.7 to 27 GeV. There are 3 sets of data points. The BES-I is showing us squares, square squares. You can see probably in the high order, the error bar is very large. And the BES-II, as I mentioned, we have 2 sets of data points. The diamond, blue diamonds is ref-3, and the red dots are the ref-3x. You can see the C1, no brainer, there's line on top of each other. That's by definition. C2, C3, C4, they're generally there's this kind of a close to linear dependence, but you can start to notice there's still minor difference. I'll show the ratios later on, you'll see clearly. But this is just to give you a general view of all the measurement we have. In the 27 GeV, because we don't have the ITPC, this was taken in the 2018 one, so there was no ref-3x data points in the new measurement, no red data points. So we look at, then we construct the ratio C2 over C1, C3 over C2, C3 over C2 as function of the collision centrality in different energies. And you can see there's a very, now with a significant improved precision, there's also very smooth dependence when you look at the centrality dependence. Particularly for the C4 over C2, that's one of the focused observable. You can see the red and blue, they have much reduced error bars. And one thing I mentioned regarding the centrality resolution impact, because we have a high, you can say hierarchy, the ref-3x from BES-II, the multiplicity is larger than the ref-3 BES-II is larger than ref-3 BES-I. The expectation is this on this cumulative ratio, there's also the hierarchy. The better resolution, this ratio is getting a little reduced. You can see the open circle, blue triangle, and the red dots. And those qualitatively, it is also can be seen using the model study. This is actually a European model simulation from 7.7 GeV. We tried different multiplicity choices. ref-3 in the green red, the squares are the ref-3x. In each scenario, we also try to apply an arbitrary efficiency as well. And so the multiplicity ordering is basically you have the blue larger than pink, larger than red, larger than green. And if you look at the cumulative ratios, you see this ordering also the ratios with better resolution, your ratios start to decrease as well. So qualitatively, that's a trend that I think it's consistent. Quantitatively, certainly that I think will still need to be continued to discuss. It depends on really how the resolution. Yep.
Why the centrality resolution is so important? Is it because you want to limit the fluctuation in volume?
That's exactly one of the purpose. And
But they are sort of cancelled if you do the ratio there.
Not necessarily. There are different orders. The effect will be different. So there's a residual contribution. That's one of the things that in all the fluctuation measurement that we need to.
But there's only certain limit because even though you have precise resolution, there's always fluctuation. Yeah. Intrinsic fluctuation.
Yeah,
that cannot.
The best is to detect all the particles, right? And what's the limit? That's what we're looking to. So. Okay, so now can show the results, and one of the kind of highlight observable is a C4 over C2. as a function of collision energy in central collisions. What shown here is actually both central and peripheral. The gray data points are the BES-I, and the new BES-II data points are the red circles. You can see now, particularly for the central collisions, air bar is much reduced. It's similar in the peripheral, but because air bar is not visible, so it's not obvious. If you compare we do a consistency check, you can see that BES-II are fully consistent with BES-I with much improved precision. And let's discuss those figures. And then this is the same figure, and the previous plot I mentioned using the RefMOS-3 to have a fair comparison with BES-I. And now we see the BES-II RefMOS-3 and the BES-II RefMOS-3X. There's a they are in the central collisions. They are very compatible with each other. This is actually we see in many other observables. That seems basically the centrality resolution effect is become very small or little in the central collision for the C4 over C2 observable. That's also one of the reasons why I want to focus on this. I forgot to emphasize that this is also seen in the ERCMD model studies. In the C4 over C2, you can see all different color data points. They are very close to each other. This is partially because also there's a cancellation in the fourth order cumulants that suppress the impact of the centrality resolution on this observable. So this point basically, this is actually one of the reasons why we're interested in focus on this observable. They're not very sensitive to the centrality resolution for central collisions.
So the error bars for the red ones are, I thought that shouldn't the systematic errors be smaller for the RefMOS-3X?
The systematic error bar assessed here is only detector effect.
I see.
There's no, we didn't do any assessment.
Because the statistical error probably is the same, because you have the same number of events. Right?
The systematic error
so where would I see the improvement, which I obviously should be there, right? But in another system.
No, the improvement compared to what? This two?
To the between the RefMOS-3 and 3X.
Well, it's that give you basically the RefMOS-3X. You have in this observable, I think we argue that actually they are very close for the central collisions. Actually, that's also the reason that this variable, the C4 of C2 in central collisions doesn't does not affect much. But for mid-central collisions, there's a size wave. There's a you can see.
Also for peripheral.
Yeah, peripheral.
Oh, yeah, sure.
Peripheral certainly. To non-central collisions, you can clearly see the difference between these two. Yeah. That's an impact. That's
all right.
Yeah.
This, I'm sorry, the last one. The bottom row is more central. I mean, the last.
This is a central collision in circles.
The last slide. I mean, the last where you have 3 rows.
Oh, 3 rows.
Go back. Yeah, this last row is.
This is a C4 over C2.
Oh, C4.
Centrality dependence. Yeah, and for different. Why is?
Okay. Yeah. So when you forward 3 slides, so if you go forward, so with your new result too. The error bar must be systematic, not statistic, right?
The bars are statistical error bars. Systematic are shown as boxes.
Why don't understand why peripheral events the error bar is smaller than central? I assume that you have more particles in central events.
Yeah, but
statistical error bar should be smaller.
That's for the C1. For any yield measurement, that's the case. But all cumulant, high order cumulants, the error bars you can see here.
The error bar is proportional to the number of particles.
They also depend on your distribution, the width of your distribution. So in the peripheral collision, everything gets pushed down to close to 0, so your error bar is very small. And this becomes sizable when you're moving away from central collision, from peripheral collision.
Yes.
I'm a bit stuck on this plot of the cumulants versus the centrality resolution.
Okay. Maybe just show this plot.
Well, no, you had another one where you improved the resolution.
In the model studies.
The model studies, yeah,
Okay.
so I intuitive, I mean, it's a simple understanding, basically you have a narrower class of physics events. And so you basically, I mean, if you have poor centrality resolution, you're mixing stuff that doesn't really belong together. So if you improve your centrality, that's really what it is.
Yeah.
So how do you know you've reached the limit here?
We don't know. That's what they're looking for. But what we want to say here, this is with our experimental limit now, the best we have. And what I want to show is, so from this model studies, we understand the difference is largely due to the resolution. Even if it's qualitative exactly, I think we still need to be determined. But the trend is reproduced from all the model studies. Whether this will reach the limit, we can do better. That's a very good question. And we are doing some of the studies using the model to push out the acceptance window. That will be helpful for us in the future, but currently that's all we have. And the limit of acceptance.
No trick you can use if you know the effect, and you don't want to base on the model studies. So no means of extrapolating to the perfect resolution.
From the earlier model studies, we kind of see that it saturates as you increase the interval.
We don't see saturation yet.
We
see decrease. We don't see
continuous
saturation.
decreasing.
Yeah, decreasing the rate, it becomes slower. We don't see saturation.
The saturation you talk about is a test with data, but that's go beyond our acceptance. So the testing saturation.
Separate question. What's the limit on your centrality resolution? What's determining your centrality resolution right now?
Multiplicity. That's with this current, I think. Qualitatively, basically, if you have more kind of reconstruct tracks used for centrality determination, you have a better.
Basically, it's a statistical limit.
Yes, it's statistical limit, and
for example,
but that's something you can deal with because you know how statistics go.
Yes. For example, now we top 5% is the most central. If we have enough events, we can go to top 1%. And we get crazy, like at least we go to 0.5%. Right? We cannot do that now with fourth order.
But are you going to get more data? You're not going to get more data.
No.
No.
That's why I think all this discussion is academic for this resolution.
I don't have a solution. If it's statistical, must be some trick you can play. I don't know.
there's always a limit, and there's an intrinsic fluctuation.
No, I understand. You want to get to the intrinsic fluctuations. You don't want it to be statistics you can deal with.
Yeah, but the difficulty is also intrinsic fluctuation. That's more dependent.
Okay.
Okay.
Lou said it's academic, so let's go on.
That's also discussing how we do it in the future. Right? Help us.
PP19. I mean, yes.
19.
Central dependence. Yeah. For example, 17.3 C2, C4 or C2 here non-monotonic dependence as a function of centrality or a function of part.
You're talking about
this one.
And there's the 5 to 10% is a little bit up.
Yeah.
We checked this from data. There's no obvious trend, but I don't think you can argue too much. You can see the error bar here. This is probably on the order of 1 sigma or a little bit larger than 1 sigma effect deviation. But this is actually one of the interesting we're still looking to whether there's any development in the model.
Let's discuss after the talk.
Yeah, we can discuss more.
Good night.
Okay, so let's do some, how do we understand from this data? So this is the ratios, C2 over C1, C3 over C2, C4 over C2. I grab Ash's presentation from CPOD, but make it large so you can see better. And then start to compare various models. This is the reference models. URQMD and HRG-CE are the same model I showed in the earlier with BES-I. The hydro model is basically validous new calculations. Including the leading contribution here is just baryon number conservation. I will show a comparison with the excluded. So yeah, so the new data points as a red connected with the BES-I in the high energies. You can see that this is the C2 or C1, C2 are the three or the smooth dependence. Focusing on C4 over C2, you can see that compared to this, there is a deviation and if we combine this together, I'll show the quantitative deviation at around 20 GeV. And as I mentioned, this and the trend, energy dependence trend, is driven by the baryon number conservation so far. And so
is this hydro equilibrium or?
No. It's just hydro and baryon number conservation. There's another calculation. I hope Xin shows it.
I have that in the next slide. Right?
Okay.
And in the coming slide. So as I mentioned, we have the we also do the factorial accumulant calculation. This is can be calculated for proton and proton separately, and they're shown as the numbers are the antiprotons and the dots, the circles are the protons. This is the kappa 2 over kappa 1. This is third order kappa 3 over kappa 1. This is the fourth order kappa 4 over kappa 1. This factorial accumulant is proposed that is more sensitive to that correlation at a specific order and fourth order correlation. So it's worthwhile also take a look. And
What would a critical point look like in this?
it's also similar feature. It would be an oscillation because of actually the prediction prefers now after discussion that will show up more in these quantities. But if for the cumulant is happening in the case if the cumulant that order cumulant is dominant in this factorial accumulants order. And so I think quantitatively is all need to be further studied. So it's a similar feature that you're looking for some oscillations. And the baseline for
the hydro model, is this hydro with some kind of given equation state? Or what kind of?
So this is Jun's hydro tuned to get the single particle data right, and then.
Do they have like a phase transition, first order, second
No.
order?
It's just a lattice QCD phase.
That's
Wait.
What is it called? Music, right? I mean, it's Jun's hydro.
So it's not really with built-in like a.
No. There's not. I mean, it's.
so
Okay.
yeah, so that's exactly we do this so-called references all non-critical based references. They don't have any critical point-induced fluctuations, and we're looking for deviation from this.
But you can ask what would happen if you put first order phase transition.
Well, there's another
That's,
plot. Then you just fit then the equation, the fluctuations also to the lattice, and then you will see that it almost goes to the data, which is not big, but we will see this.
So
then you can claim it goes through the data.
It's a prediction. We don't fix things, right? I mean, that was calculated.
200 GeV in your paper is a fit using lattice equation of state.
So we will look at this.
yeah.
Yes.
So if you look at all, actually, this is probably point out during discussion Z part, the antiproton certainly is all, it looks all close to the baseline, which is 0, and here the magenta. But protons, there's an interesting feature that they're all deviate from the for all orders actually. And there seem to be some non-monotonic behavior, but those are all you can do statistical test on the significance, and so that's what I guess Walker is looking for. This C2 C1 is no difference.
That's surprising, right? That will check.
And C3 over C2 also deviate at low energies.
Not the with the EV is the.
Yeah. The this one is better actually.
Oh, C3, no.
C3?
Yeah, that's right. But I want to look at the factorial cumulants, right? And what you see is it goes through the factorial cumulants, except for the lowest 2 points, right?
Yeah, well, getting closer, yeah.
Yeah.
Ones, yes.
Right? And now, because your 3 GeV kappa 3 over kappa 1 is down in the basement negative. So my question is, what are we seeing? Are we seeing some boring? So the blue line is now where you actually make sure that the measured cumulants from the lattice are sort of taken into account when you do your thermodynamics. And now the question is, if this is true, then you would suggest something totally interesting or different happens below whatever 9 GeV or whatever this point is, right? So the 9 and 7 GeV and 3 GeV goes all the way down, right? Yeah. So this is a different interpretation, right? And the same for the kappa 2 over kappa 1, the last 2 points are off all of a sudden, right?
I have to go to another appointment at 11, but maybe I can ask a question right now.
Sure.
Instead of looking for this up and down energy dependence, can you do similar like a Bayesian analysis, like what Scott Pratt have done? For each energy, you just use all the data available and give you constraint of equation of state, and see what happens when the trend.
Just do a conventional analysis of.
So
Yeah, because they have done this at high energy, right? And then can you do for each energy do this similar analysis and look at the change of the equation of state you get at different energy?
That's certainly a very good point. Maybe Volker can comment, but my understanding is now certainly if you put a critical point or first order phase equation state there, how do you translate it into the proton fluctuation?
I assume you can do the model right.
That's the model still. I don't know whether it's ready or it's still under being cooked, and that's a very
So
challenging.
what could be done is what Bologna has done, which is only stuff which we know how to deal with.
Yeah.
But if you want to put a critical point in, we are not there yet how to do this in hydro.
Well, I'm just not necessarily critical point, but maybe I can see the change at high energy versus low energy. If we suddenly see from crossover to first order phase transition, then there is, even if we don't see the critical endpoint, and there is clearly something between, right?
Sure. Yeah.
The thing is that do you see like at low energy there is the equation state typically is really first order versus the crossover at high energy?
So I think we can fairly say those calculations that's based on the just crossover phase transition.
Right.
We see deviations in the low energies.
Yeah, exactly.
But how quantitatively by putting the first order transition whether it can reproduce data, that's.
I mean, this needs to be done. My guess is if you fiddle with the equation of state only, you won't change much here. But this is my guess. But it needs to be done. You're absolutely right.
Well, yeah.
I confess to be getting confused thinking about proton fluctuations at these very low energies. You've got another thing which is proton number. By definition, these collisions have large U, and you deduce that because they have a lot of protons, and they have a lot of protons because there's not a lot of longitudinal phase space. And so you've got all this complicated proton stopping stuff which has nothing to do with thermodynamics, nothing to do with the critical point. It's just how do you transport protons from the beam into the central region. And the central region for these high mu-B guys is pretty substantial part of the total phase space. And I could who knows what nature does? There could be correlations in the way protons stop. I mean, how do you disentangle all this?
I think it is certainly microscopically. I think that's certainly the dynamics you would see. But if you have a kind of some finite hot medium created with finite temperature density, your proton going through this medium, or no matter where, it will feel the effect. That's also the dynamics we're looking to, basically. That's my opinion. And that's also we at least in the energy we're looking for here. Those are the middle energy, very central. We focus on the central region. There could be also nuclei protons that's coming, and also up to 7.7 GeV. 7.7 GeV, the beam rapidity, I believe it's 2.5, 2.7.
Still some distance away.
Yeah.
So, and the difference between proton and antiproton, of course, is the difference.
Right.
Although, even if bare numbers conserved, even antiprotons could have some residual fluctuations from the stopping stuff.
So we, in the old star data, the BES-I data, we could not get the antiprotons by no means. We haven't looked yet at the new data. I don't know how much they changed, right? So indeed, but in the olden days, what we tried to estimate this stopping fluctuations, that was when we still had the old 7 GeV huge signal, which then got revised. And there, compared to this signal, the effect of stopping fluctuations was minute. That's why we didn't look at this. But now that I have much smaller signals, we have.
So you try to model this.
Yeah, we tried, but now we have to go back because now I don't have to look at a C4 over C2. What was it? 3.5. Now I have better data, much better data, thanks to the star collaboration, and the signals are much smaller. So all of a sudden, this could actually be relevant. What you were saying.
Could one do it in rapidity slices, which correspond to mu slices? Is the
That's
same,
one
in
of
the same
the
system?
kind of future direction I'll be talking to.
Let you finish, do the physics slides.
Yeah.
Please, go ahead.
Yeah, okay, I have
You will mention the physics.
we have a couple of slides on the future. So let's try to quantify the difference. That's collaboration also works out to see. And this is the same plot. I put X3G, the points included that. Actually, I should put it. And you can see the trend actually. The reference basically, when you go to low energies, due to baryon conservation, this actually goes down dramatically. And if we this right plot, if we so because this reference actually is not flat across energies. If we take the ratio of the data of the model, and this is just replotting the data points and take the ratio, and that's what you call this. You see still the minimum. That's what you see here, around 20 GeV, and those different models are different, as we showed here and before, and the deviation at the maximum level is probably 3.2 to 4.7 sigma here at 19 GeV, and the overall deviation, if you take all the data points together, is probably 1.9 to 5.4 sigma, depending on which reference you choose. And if we quantify the residual, basically is the data of a model divided by error. That's the quantity actually we're looking to. And we also put 3 GeV data points here. This is also half rapidity, but it's fully compatible with the RHIC calculation. This 3 GeV. So that's actually I think the data is we really look into the development from our theory side how to understand this data. And
just very quickly on the last one, the low points, especially the ones with smaller uncertainties, are those dominated by the statistics? I'm looking at the left where you've got the error bar.
Oh, this one, it is dominated by this one?
No, I'm sorry.
This one, yeah, this is still dominated by statistics. The systematics is actually a factor 2 to 3 smaller.
I just realized the correlation of that might matter. Okay.
Right. And this error is a combination of a total statistics and systematics. So actually interesting, I think Peter brought up is baryon dynamics in the low collision energy. We see also the behavior change in many other observables. This is looking for the baryon string correlation, kind of cross term in the second order, normed by the strangest number fluctuation. We now have capability to looking for including proton, kaon, and lambda together. And this is also central collisions. And the data points actually see in the high energies is consistent with lattice and also this function FRG model calculation with this crossover phase trend in the high energies. But in the low energy, you can see the start increasing and deviating from FRG. But URMD start to capture with this hadronic transfer. So actually, you can see the deviation in the low energies. Similarly, this is the proton, so-called excess proton V1. Well, presumably it's kind of one way to separate this medium effects out, but looking for the proton dynamic goes through the medium. And this quantity, if you look at the slope parameter, it's actually pretty flat at 14.46 GeV above following this scaling, but it starts to deviate at low energies. So all this data actually also fresh. These are just reported recently in the report.
I would like to make a point here. Xin is not here. There's no model now can calculate V1. Okay, don't mention we add into first order. Just the simple V1 you cannot reproduce. And how do you do Bayesian? I don't know. There's no reliable model to calculate that. It's also your job too. So it's quite to me a big issue.
Okay. Yeah. Let me summarize and spend a few minutes talk about what we plan to do in the next. So we have the precision now measurements from BES-II with better statistics, better systematics, better control resolution. So the take-home message is really we have now basically the BES-II. We kind of it's a great success. We deliver results the precision as we projected, and including both statistics and systematics. Data show that I would say it's 3 sigma above. It's evidence of a minimum around 20 GeV. Compare the different reference models, but certainly these will be continue developed with our theory friend to see how we can understand better and how this can tell us regarding the QCD critical point.
So publication submitted?
So currently we are preparing a manuscript. Hopefully within a month or two should be able to discuss with the STAR. And I think we really aim to really very speed publication, very speed submission.
To Nature, to Chirality?
We are having to think about it. That's PRL is
great now.
yeah, I don't have a good. I'm not a super enthusiast to go for nature this moment.
That's for biologists. Please not for me.
No Nobel Prize in Physics was published in Nature.
Oh, that's.
Okay. Yeah, let me talk a little bit about what we plan to do. A few outlook. Those, as I mentioned, I think Peter also mentioned the rapidity scan. It's also critical, and we started currently using the same acceptance we did before, which we sure with plenty of sufficient statistics and also the uniform acceptance within that region. And with our ITPC, we can certainly push this further away, but this we have to limit your VZ region, as certainly this eta VZ are correlated, right? So if you want to have uniform acceptance up to 0.7, you have to limit the VZ to 50 centimeters. So we are doing that, but
that would reduce your statistics by how much?
Square root of 3/10. So that's our vertex distribution is pretty much flat in low energy, so we can easily scale this just to the VZ window size. So this is still BES-I data points. We didn't show this, but we should. That's what we're working on, to looking for the PT rapidity dependence and possibly pushes our forward in the higher region.
Can I ask a completely off the wall question? This is a question that is new. What's mu B in the LHCb acceptance? Very forward at the LHC.
I reviewed a proposal by them. It's comparable with, give or take, if I remember right, 60 GeV RHIC data. So they have a program. I'm not sure whether this gets realized.
That's only 6 target is smaller.
Yeah, I think so. Yes.
No, I was thinking. Well, that's different. I was thinking in collisions, nuclear collisions. They just go to, central region, forget it.
Yeah.
But you go very forward, because there is a profile of barium stopping at the LHC. Extremely forward, go to rapidity, I don't know, they can go to rapidity 4, say. What's the net baryon number at rapidity 4? And what's the corresponding mu?
I don't think they can do it. Same thing.
They may not have the proton identification, I'm just asking the physics.
You need the acceptance to do high order correlation.
It's got like 3 units of Y.
PT, this is the, we're struggling with this. This black box we draw like for 15 years, right?
Yeah.
Trying to expand a little bit.
So maybe this is something for Alice 3 to think of. Okay, forget LHCb. An ideal, money is no object. You build the ideal, very forward detector with excellent proton ID at the LHC where mu V is non-zero.
Yes.
What can you do?
If you have rapidity 5 in at least 3, with this coverage, TT to 2 GeV, I'll be there. Okay? Simple enough. You cannot. I know that. Because immediately at that rapidity, I look at at least 3 very closely. This still only works at the middle. Okay. It's actually really important. Then next one is efficiency. Homogeneous efficiency.
I told you, money is no object. Okay, good. We can move on. That's not gonna work.
Second thing we're looking for further hyperorder. It's actually should work, and the precision on the C4 is actually quite decent now, and we should be able to continue looking for the C5, C6. This is the high orders I predict to be also more sensitive to the thermodynamics of this system, and the light scarcity predicted in the crossover phase transition. This will have a continuous decreasing trend when you going down to low energies. And in the BES-I, we see this general trend, and the 3 GeV is up here. So this kind of a non-mounting feature, and we are aiming to further reduce this error bus, and also that will help understanding to have a global picture on how this phase transition looks like. So furthermore, we have the collider energies, as mentioned, that we if we look at all these distributions now, and really you're thinking about whether there's any oscillation feature that need to get low energy coverage, and BES-II has the data covering energy, although it's across broad energies.
These are data on tape.
Data on tape, and but I'll show the next slide immediately. For the millimeter coverage for protons, we only have roughly this 3 GeV to 4.5 GeV. That is shown here actually from Zach. The PT versus the center mass frame proton rapidity from 3.2 to 4.5. 3.2 is no problem. We can even cover the positive rapidity region. And when you're moving towards higher energies, the acceptance gets pushed out. At 4.5, you start to see the still have, and also there's a gap between baryonic and ETOF, because you need to rely on the time flight to identify protons. And then the gap also need to be understood and taken care when we try to understand this effect. So that's actually, we are also working on in STAR, trying to get this, that's the kind of next priority as well, to get this results out. That's why we still not ready. There's complication wise acceptance, and also detector-wise, there's also so-called pile-up and the pile-up effect we need to understand. In the meantime, this volume fluctuation and the low energy become more severe, and that's the physics reason that also need to be further understood. So the centrality resolution, I think I don't want to talk too much. This is low energies in our 3 GeV publication. We showed that the data points, if you're using different models for the volume fluctuation, you end up quite different values for mid-central collisions. But central collision actually is a nice, these values converge, but still to have a global understanding, this is okay. Thank you. So I'll just end up with this slide. I don't think I need to say more. That's all the future high UV experiment. Still, I think will push not statistics further high to get reduce the error bars and the control systematics that hopefully can also help in the nature of this QCD phase error.
Thank you, Xin.
Thank you. Congratulations to STAR and the team for this fantastic data. You guys really delivered. Now we have to figure out what they say, but the data are great.
Thank you.
Yes. Please,
guys, go back one slide. Just one for the one more, please. Cautious on the.
This one?
We are struggling on 4.5 GeV. Personally, I'm not sure. For 3.9, I think.
Why is 4.5 different? I mean, you have always this sliver there in the middle, which worries me like hell.
That effect is not that big. We already have simulation. At this low energy, we need a time of flight to cover. We need a similar coverage of TTC and time of flight in order to have proper centrality definition and the proton identification. If they are not mismatched, we have to be really careful because the time response of TTC and the top are different. We may select a different class of event mixed. So that is very difficult. And you see there's no overlap.
Yes.
In 4.5 GeV. In 3.9, we still have some overlap, and we can do cross.
So I see.
Yeah, so this is, we are struggling.
But we can also play these games where we change these dynamic and signal cuts, and we can really push the TBC acceptance to farther than what is being shown here.
Yeah, if we can do that, that will be great. So at the moment, I'm not convinced. In addition, there's also pile-up. We need to suppress that. Pile-up is most severe for most central cases. So those are the strugglings.
Can I have a question?
Yes.
With your slide with the the n sigma away from the baseline.
This one?
Yeah. So you have these n sigma that are 0 to 5%, but you also have these faint points that are half opaque.
This one?
Yeah, and these are the 70 to 80%, and they also show us a large deviation.
No. This is using the 70 to 80% collision as a reference, basically the central with respect to the 70 to 80%. That's one of the choice for reference. I think if we assume that 70 to 80 is just a plain no critical point.
If you use 70 to 80% data as a reference, there is no positive point. It's always below zero.
Yeah, because you can see clearly, it's also obvious here. Data points higher. And
right. I'm looking for another bump below 7.7. We need more data. That's why
It's going down, right? I mean, it's already shocking how far down it is, and you see the 3GV1, right? So the kappa 4 will go down. I mean, the KC4, right? That's my prediction.
If go down, it's fine. We already have, you can imagine the simulations in this range.
Right.
The question is data go similarly with simulation or go
Yeah,
slower or go faster? That is the question.
yeah, Walker, this is actually only half of it.
I know. I always complain that you put this on the same plot. I'm very much. Yeah. Anyway, I'm very much aware.
Next time, I think once we look at this, probably not in terms of energy, because this is very sharp, and BV probably very. Okay, thank you.
Very good.
Okay. On the Zoom, it's a V.
Can I get the slides? Are the slides available? Or is it something?
Yeah, I'll send you
Okay.
one link.
Okay, very good.
Or you can go to
Super.
YouTube.
YouTube, okay, you have the record.
Oh, that's a.
Yeah, where are you?
Oh, you better.
Are you on the way or you are in the middle of
So.
this? Okay, thank you. See you later. And congratulations.